Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the Lagrangian and the Eulerian perspectives of flow, and we will also look at the fluid element trajectories. The concepts that would be covered include the two different perspectives of flow analysis. We would talk about a few techniques for analyzing fluid flows, and we will also discuss about fluid element trajectories including streamlines, path lines and streak lines. And here are the key points for this lecture. So, let us begin the discussion by looking at the Cartesian vector form of a velocity field which varies in space and time. So, we can see that a velocity field has been mentioned over here, indicated by capital V, which indicates a vector, and it is comprised of three components: small u, small v and w. These are the three components it is comprised of. Okay. And additionally, what we notice is that each of these components are dependent on x, y, z and t. That means, the spatial location of the point as well as time. So, in general, this velocity vector can vary with space and time. And then we have the associated unit vectors I, j and k for the respective directions. So, this is how it is done for a Cartesian velocity field. If you are looking at other orthogonal coordinates like cylindrical polar or spherical coordinates, you will have corresponding components of the velocity along the respective directions in those coordinate systems. Now, till the last lecture, we were mainly emphasizing about pressure and shear stress distribution on a body, and we remember that the pressure and shear stress distribution on a body is developed by virtue of the flow velocity. So, if the velocity exists, you have a distribution of these two parameters. If the velocity ceases to exist, that means the flow comes to a stop. That means, you have a static situation without any dynamic flow around the body of interest. The body would experience uniform pressure equal to that of the ambient, and it will be felt equally all around it, and the shear stress would be equal to 0. There would be no friction felt because there is no flow occurring past the body, and therefore, the shear stress vanishes altogether. Therefore, pressure and shear stress, which we integrated in the last lecture to obtain the forces and moments etc., the distributions are created as long as you have a flow velocity. So, the domain of aerodynamics basically concentrates on situation where there is a flow velocity existing, and therefore, defining the flow velocity in a manner like this is an essential part of the study. So, here in a Cartesian system, we are seeing the three components of velocity. Now, let us suppose that we are standing on the floor of a laboratory. So, when we are doing a course on aerodynamics, we would be in an aerodynamics laboratory, and we are observing the air as it passes by through the test section of a wind tunnel. So, a few lectures back, we had seen a few photographs of wind tunnels, and we recall that the heart of the wind tunnel is its test section. That is where the models are located, that is where the measurements are made. So, we are standing on the floor of the laboratory and we are performing some experiments. So, to begin with, we are observing the air by some means, and we are seeing as it passes by through the test section of a wind tunnel. A set of coordinate lines have been drawn on the glass window of the wind tunnel test section to define the observer's fixed coordinates. So, when we are the observers, we have our own coordinates that is fixed. This is the Eulerian frame of reference. That means, we as fixed observers, we are observing the flow going past us. The Eulerian system can be visualized as a window through which we watch a flow, right. So, we do not change our own location, we just define a certain domain of interest and we just observe the flow moving into that domain and moving out of it. The coordinates of the observation point, let us say x naught, y naught, z naught, they are fixed and the flow passes by. A fixed instrument placed in the flow takes an Eulerian measurement. Let us say we will look at instruments like pitot-static tube later on. So, such instruments are fixed to the tunnel walls and therefore, they are looking at the flow just like us as the observers, and therefore, it is making an Eulerian measurement. On the other hand, Lagrangian coordinates follow the moving air particles. This approach is of course, more often used in solid mechanics, but we do need this concept even in fluid mechanics, and if we are following the fluid particles, then we are taking a Lagrangian approach. So, if you really want to distinguish between the two approaches, an example can be cited that an engineer who is studying traffic flow in the roads will remain fixed and will measure the flow of cars going by from the point of observation, and that is an Eulerian viewpoint. And then conversely, the traffic engineer notices that some city police are following specific cars as a function of time. So, the city police would have a Lagrangian viewpoint of the moving vehicles. Let us briefly discuss about some flow analysis techniques. There are essentially three basic techniques to analyze a fluid flow problem. First one is a control volume or integral equation approach, where in the flow field in some location we define a finite volume encompassing some space, and the boundary of that volume is the control surface. You can see that it is immersed in a flow field. These different lines that we have drawn with arrows, they are streamlines of the flow, which we will discuss soon. So, they gave a feeling that the flow is moving its way, it is making its way through the control volume, it is entering the control volume through some part of its control surface and then moving through the control volume and then finally leaving it through another part of its control surface. So, that is basically the concept of control volume. And then we may have a small fluid element, we have defined it through a small cuboid which is located somewhere in the flow field. Again we see the same streamlines, and then the fluid element it is making its way through the flow. So, the control volume, as we discussed over here, appears to be a fixed control volume, while a fluid element here is apparently a moving fluid element. But you could also have other situations where the control volume itself is moving through the flow field, or the small fluid element is also fixed in the flow field. The location is kept fixed, though it remains a very small element, and we then monitor the flow through that small fluid element. So, those are the two approaches. So, control volume is an integral approach. We have a large volume and we are essentially measuring the flow parameters as it enters, moves through the control volumes and leaves it, while as far as the fluid element is concerned, it is a very small volume. So, it is an infinitesimal system, and we would take a differential equation approach when we look at such a small system. So, it is an integral approach here, while a differential equation based approach here. On the other hand, in experimental studies, we essentially look at dimensional analysis approach. So, these are broadly three different techniques that we use for analyzing fluid flow problems. And then when we get into any specific approach, this flow satisfies Newton's laws of motion, it has a thermodynamic state relation which it satisfies, and it also satisfies associated boundary conditions depending on the kind of flow problem that you are solving. So, it has to solve the flow problem by maintaining certain constraints. For example, mass conservation has to be maintained, has to be assured under any circumstances. So, that comes through what is called as a continuity equation. The momentum conservation comes in through the application of Newton's second law to a fluid volume. So, that conserves linear momentum. The first law of thermodynamics, which talks about the conservation of energy, the thermodynamic state relation, which could be something of this sort, that pressure is expressed as a function of density and temperature, and then appropriate boundary conditions. You would have the flow coming in through some regions of the control surface if you are following a control volume approach. So, those portions would be called as inlets, certain portions of the surface through which it leaves, which will be called as outlets. There may be solid bodies inside the control volume like an airfoil. So, you would be seeing the flow moving past solid surfaces. There could be also interfaces. In integral and differential analysis, these 5 relations that we talked about over here are modeled mathematically, and they are solved by using computational means. While in an experimental study, the fluid itself performs this task automatically. We do not have to take care of the mathematics, only observations have to be recorded using suitable measurement instruments. We will spend some good time on fluid element trajectories now. So, we are going to classify them to begin with into 3 categories when we begin. So, there are 3 types of fluid element trajectories primarily. Let us take note of the names first: streamlines, which we just talked about in the previous slide, then path lines and streak lines. So, there are 3 different terms that we are talking about. We have to remember these terms and we have to understand their significance in a flow field. So, these trajectories are all equivalent for steady flows. Steady flows are those which do not change with time, they are time invariant. But these trajectories would be different from each other if we are looking at unsteady flows, that means where there is a time dependence. So, as we formulate the 3 approaches of looking at fluid element movement, defining their trajectories, we will understand very soon why they differ when time comes in. Let us define streamlines. A streamline is defined as a line which is everywhere parallel to the local flow velocity vector. So, we already defined the flow velocity vector in an earlier slide. Here we are just mentioning the components u, v, w. As you can understand that these u, v, w's could be either function of space alone if it is a steady flow, and would be a function of space and time if it is an unsteady flow. Now, let us assume this streamline to be a curve. If you remember in the previous slide also, we had drawn a couple of them like this when they were moving through the control volume with arrows. So, we are just drawing one of them, let us say over here with an arrow, and let us define an infinitesimal vector along that streamline. So, we pick a point and we define a very small vector ds along the streamline. So, it would have differential length scales involved along the 3 directions. I, j, k are the unit vectors along x, y, z directions, and these are the length scales involved associated with that infinitesimal vector. Now, since this vector is parallel to the velocity vector, that is this vector. So, d s is parallel to the velocity vector. They must satisfy the criterion that the cross product of the 2 vectors should go to 0. Now, let us say you have a vector A and another one B, which are both parallel to each other, and let us say they are along the x direction. So, you would define A as its modulus times I and B also in a similar manner like this. Now, you know that if you take a cross product of the 2 vectors, they will go to 0, because I cross I goes to 0. However, if you take cross products of orthogonal vectors, here we are taking 2 unit vectors along x and y directions, and we are taking a cross product. By the right hand rule, it will give k. K is the unit vector along z direction, which is orthogonal to the plane containing the I and j vectors, which is the xy plane. Similarly, j cross k will give you I, and say k cross I will give you j. Let us look at vector cross product in some more detail. So, if we take 2 vectors A and B with their 3 components a x, a y, a z for the A vector and b x, b y, b z for the B vector. When we take a cross product of the 2, we can define this determinant, where the first row comprises of those unit vectors I, j, k. The second row comprises of the elements of the A vector, the third row elements of the B vector, and then you expand the determinant, you get 3 components like this, associated with the unit vectors I, j and k. Now, using this result, we can very easily check what would be the outcome of this cross product d s cross v. So, that will yield this relation. Remember that v is nothing but u I plus v j plus w k, and d s comprises of d x I plus d y j plus d z k. So, now you can take term by term and compare between this result and what you have at the bottom. So, you have 3 components here in the cross product d s cross v, and they all individually should go to 0, so that you ultimately get a 0 as an outcome. So, each of the components of the above vector should be individually 0 to satisfy the equation. So, we have written the components here. So, they give 3 differential equations which define the streamline. Now, the 3 velocity components u, v, w must be given as functions of x, y, z for a steady flow field to integrate these differential equations, or if it is an unsteady field, then as functions of x, y, z and t. So, only then can you integrate the relation to obtain the streamline equation. Now, to obtain the values of the integration constants, when you perform the integration, the coordinates of some point lying on the streamline has to be provided. And one has to also ensure that the flow must have crossed that point at a specific time. So, that time has to be stated. So, this will form what is called as the initial condition. so that you can perform the exercise to obtain the equation of the streamline. So, since streamlines are everywhere tangential to the fluid velocity vector, it must follow that over an infinitesimal interval of time dt, a particle of fluid would be displaced by increments dx, dy, dz in the 3 directions x, y, z, where these incremental displacements would all satisfy these relations. Dx is equal to u dt, dy equal to v dt, dz equal to w dt. We will do a little more detailing on streamlines. So, it must be clear to you already that we could have streamlines defined both in 2D and 3D space. It is much easier to do it in 2D though. So, let us say if it is in the xy plane that you are looking at a streamline, you have the x naught, y naught coordinates through which the streamline crosses, say at t equal to 0, and then you follow the streamline. So, if you are at a certain point on the streamline, you would notice that you can draw a small region around that point with dx and dy lengths along the 2 directions, and you will see that the velocity components which exist at that point and the elemental vector ds that you can draw at that point, they are parallel to each other. So, the dx and dy combination basically defines the ds there, and the v is the longer velocity, the vector which is comprised of the components. I am sorry, the v vector ends here. So, this is the v component. So, the basic idea is that ds and v are parallel to each other. Okay. So, if you were to look at this picture in 3D, then you have the xy plane and the z. You similarly have a starting point here, x naught, y naught, z naught, let us say, and you have a streamline moving through the 3-dimensional space. Again, along that line, if you take up a certain point, you can define a ds, and you will find that the v vector remains parallel to ds even in a 3-dimensional situation. So, this is how you can look at a streamline in 2D or 3D space. You can also look at a concept of stream tubes, where again let us look at it from a 3-dimensional perspective. You look at a couple of points, let us say 4 points at some time t equal to 0, and you follow the streamlines which move through those points and you track them over time, and at a later time you will find that you can map the points along the respective streamlines. And what you see in the process is that a tubular region gets defined, which we call as a stream tube. So, the streamlines passing through all these points form a surface. And there is no possibility of the flow crossing this surface, because the flow always remains tangential to each streamline. Therefore, whatever mass flow enters through the dotted circle containing the points 1 to 3 flow will move out of the solid curve 1 to 1 dash, 2 dash, 3 dash, 4 dash at a later point of time, and therefore, it is acting like a tube which carries the same mass flow rate. That means, there is no mass exchange possible across the stream tube. Let us keep these concepts in mind, and as we proceed further, we will keep recalling these ideas. Now, let us try to look at a simple problem. We will try to find the equation of a streamline for the following velocity field at time t equal to 0. We will later see that when we discuss path lines and streak lines, we will use the same velocity field to obtain the equations of path line and streak line as well, and then we will get back to the streamline equation and we will compare and see whether they match or are they different. So, in that context, we will say that all the above lines, which means the streamline, path line and streak line, they would be passing through the point 1 1 at time t equal to 0. So, you remember we were discussing about an initial condition. So, this gives you an initial condition basically. So, we recall that when the problem occurs in x y space, then the equation of a streamline would be given as dx by u equal to dy by v. And remember that here, because it is a 2-dimensional field, flow field in the x y coordinates, it is implicitly assumed that w is equal to 0. That means, we neither have a z dimension nor do we have a z component of velocity. All right. So, you are basically looking at the u field as a function of x, y, t in general, the v field again as a function of x, y, t in general. So, here u is this function 1 plus 4t into x, v is y. So, let us put it here, substitute it, and then we will integrate it. So, before integrating, you can cross multiply and make this dx by x equals 1 plus 4t times dy by y. When you integrate this, the 1 plus 4t is left outside the integral, you get natural log x equal to 1 plus 4t natural log y plus integration constant, which basically means you have natural log of c y to the power of 1 plus 4t Therefore, we can conclude that x is equal to C y to the power of 1 plus 4t. And then using the initial condition that the streamline passes through 1 1 at t equal to 0, the value of the integration constant can be obtained, because the initial condition gives us x is equal to 1 equals c times y, which is 1 times 1 plus 0 4 into 0, because t is equal to 0, which means c comes out to be 1. Okay. Therefore, finally, what do we get? We get the equation of the streamline at t equal to 0 comes out to be x is equal to y. So, we have discussed about the Lagrangian and the Eulerian viewpoints of a flow field. We have discussed about a few techniques by which we usually analyze flow fields, and then we have started the discussion on fluid element trajectories, where we could discuss specifically on streamlines in this lecture. In the next lecture, we will discuss about path lines and straight lines. Thank you.